Andrew Hughes presenting. He's a part of the 2011 ATS class. He's currently attending Brooklyn Technical High School and will be speaking about growth of zinc oxide nanowires. Please welcome Andrew. Please remember to ask questions after each presentation.
My name is Andrew, and my research is on growth of zinc oxide nanowires with Dr. Xu at St. John's University. In my presentation, I'll talk to you about the background of my research, the procedure, which includes pre-cleaning, seeding, growth, and electroplating, the results, future work, and uses. For background information, zinc oxide crystals have shown to take up most of the light spectrum. Its hexagonal structure also provides a strong basis for constructing nanowires. By building vertical crystals, the wires can be used for things such as viewing objects on the nanoscopic level. However, the problem is that it is hard to control zinc oxide seeds, and the wires may grow horizontally or may congregate together. The first step in the procedure is pre-cleaning. We take from a 120-gram alkaline solution, which is basically detergent water, and clean a tweezer, Teflon holder, and a 100 milliliter beaker. Because of the experiment's emphasis on cleanliness, everything is scrubbed and rinsed in both distilled and deionized water. The Teflon holder is then placed at the bottom of the beaker with the tweezers, and a gold-plated chip is placed into the Teflon holder. The beaker is then filled with 65 milliliters of acetone. The beaker is then placed in a styrofoam cutout and placed afloat in backwater in a Branson 1510, which sonicates the solution. Sonication is where sound waves are used to vibrate the solution in order to remove any dissolved gases. After the solution has been sonicated, the Teflon holder is then moved to methanol and sonicated again. And then this process is repeated with isopropyl alcohol and deionized water in order to clean the surface of the chip, and it is also because all four liquids are good solvents of each other. The second step is seeding. Seeding is where we place zinc oxide seeds onto the gold surface in order to provide a base for the nanowires. The seeding solution is a mixture of zinc acetate dihydrate with ethyl alcohol. However, the mixture varies with different chips that we use. The chip is then baked for 30 minutes in order to burn off any organic materials. And while that is happening, a pipette tip and pipette are cleaned. Then the pipette takes up a drop of the seeding solution and drops into the center of the gold chip. And then the chip is then baked for 30 minutes to help also again burn off any organic materials and help the wires grow vertically. The next step is growth. Here we take a growth solution of hexamine and zinc nitrates, which is both 20 millimolars each to form a 300 milliliter growth solution. The solution is again degassed for 10 minutes to remove any dissolved gases. It is then poured into a petri dish and placed into a hot plate. A vacuum system is then used to place the chip afloat onto the growth solution with the seeded side face down. This is to help the wires grow vertically as much as possible without any other contamination landing on it. Thermometer is then put onto the hot plate into the petri dish to keep note of the temperature throughout the time period. The hot plate is then set to a certain temperature, which is usually around 100 to 95 degrees, and is observed for 90 minutes at 10-minute intervals. During this time, we take note of the temperature, room humidity, any bubbles forming on the chip, and the growth solution. The final step is electroplating, where we simply create a complete circuit with the gold chip as the cathode and pure silver as the anode. The purpose is to plate the chip with silver so it fills the spaces between vertical nanowires. So when light passes through the nanowires, it does not escape until it reaches to the end. And this is a picture. And we use a solution of AG2460, which is basically a low gradient surface solution, which is good for plating the gold chip with silver. And these are our results. The first chip, PH84, we used a 5 millimolar solution, and we saw that there were no area clear of large non-vertical wires, which is bad, and because with non-vertical wires, light is not able to pass through it correctly and all the way. And there are voids present, which were empty, basically empty areas. The next chip is a PHB1, which is a 1 millimolar solution. We believe that if we lower the seating solution, we would be able to create more vertical wires while sacrificing the density of them. And here we saw that there are significantly less non-vertical wires than PH84, and however, there were more voids than PH84. Finally, we went to chip PHB2, where we used 1 millimolar solution again. And this time we degassed the solution because we thought that there were dissolved gases in the solution, so when we seeded it, there would be microbubbles, which caused voids. So when we observed it, we saw that there were the same amount of black dots, which are the non-vertical wires, as V1, but this was because we had accidentally dropped the chip into the countertop while seeding. However, the voids were much smaller. And here are the microscopic images of the chips. For PH84, the large circles are the voids, and the lighter gray areas are the vertical wires. You can't see them because light is passing through. And the darker gray areas are non-vertical wires. It's very hard to see because, well, it's on a large screen. You need to be up in person to see. And in PHB1 you see a network of voids as well. And then this is PHB2, which showed almost no voids and very little black dots of horizontal wires. Our future work is to work on more gold-plated chips to vary things such as the grow solution and the seeding solution or the cleaning process to make it more thorough. We're trying to achieve a chip with areas clear of non-vertical wires, voids, and avoid any contamination, which can cause ridges and cause seeds to push together. So the uses of nanowires. They can be used in LED lights by taking in a higher spectrum of light, providing better visuals. It also has potential uses in solar panels and solar cells to maximize light intake. And theoretically, it can be used to view the insides of cells without destroying it, and also with color because it can take in mostly light spectrum. And these are my references. Now I'd like to thank Dr. Shoes, Spencer, St. John's, Dr. Sanford.
Can you go back to your methodology?
My message.
What was your hypothesis?
Well, we didn't really have a hypothesis. We just we did each chip, and then we would see what's wrong with it, and we would create a hypothesis of what went wrong. And for one, we dropped it, or there was contamination before we got the chip, or maybe the seeding went wrong because we didn't seed perpendicularly to the chip.